So the order matters in a sequence. And also in a sequence, repetition does matter. Like you might have, for example, a sequence like 1, 2, 1, 3, 1, 4, 1, 5. That's a different sequence from just 1, 2, 3, 4, 5. So repetition does matter. Now a sequence, it's a list, right? List of objects. A sequence can be finite or infinite. Finite, that means there will be the last member in the sequence. It'll stop after a while. Or it can be infinite, just goes on forever. Okay? So now a finite sequence there's often a special label given to a finite sequence. It's called just a tuple, T-U-P-L-E, tuple. And if you have k elements in your sequence, a list of k things, that list, that finite list, will often get called a k tuple, because it has k elements in the sequence. So a k tuple. For example, our set that we've been using here, you could look on that. Well, the brackets are a bit different. Let's use this one. So, it's got others. Well, all right. Well, except for the brackets, this list here is a 3 tuple, right? Because it has three elements in your sequence. Now, a 2 tuple often just gets abbreviated to a pair. Right? So if you hear the word in this context, the sequence, if you hear the word pair, just think about 2 tuple. So it's just a list with two elements in sequence. Okay. Now, both sets and sequences, they can be elements of other sets and sequences. Like, for example, now here's a new concept in set theory, the so-called power set. What's that? Well, by definition, it's if you have a set A and you form the power set of set A, what you're doing is you're creating a new set, that consists of all possible subsets of A. Okay? Now, it very quickly becomes large as the number of elements in your set A increases. But let's say we just have 2 elements in set A. So find the power set of A. In other words, find all subsets, possible subsets of this set 0, 1. Well, you've got the empty set, right? Did that the previous session. It looks like a capital 0, like the number 0 with a 0 sign but a slash through it. Okay, we have the subset that's just one element. The subset of 0, the element 0. Here's another subset that consists only of the 1, and then here's the subset that's the set itself. Now this subset is not a proper subset. Remember the definition of proper subset? So how many elements do we have in this power set? 1, 2, 3, 4. Now maybe I'm not sure, but if your set has n elements, the power set will have 2 to power n elements. I don't know if that's obvious to you or not, but anyway. Okay, so there's the power set. Now, the power set was an example of sets and sequences can be members of other sets and sequences. Like, so this is a set, a set, a set, a set, they're all set, but they're members of the big set, right, the power set. And let's see, so you also have a sequence here, right? Now this is a sequence, not one. That's a 2 tuple or a pair. Now that is a member of this sequence, that. Right? So you can have sequences that are members of sequences. You can have sets that are members of sets, and so on. Right. Well, now expect for the next quite a few sessions. I'll just be throwing fairly elementary mathematical techniques at you that are tools, prerequisites for the real work. The 3 parts of the text, 400 pages. What is it? So we're talking roughly 140 pages. Is that right? Yeah, 140 pages each, roughly, on each of these 3 parts on average. So we're tool building at the moment, learning the tools and the notation that we will use in most of the text, and this will go on for quite some weeks. Probably the most valuable, well, it's debatable, but probably the most valuable part of these tools that we'll learn are proof techniques, like tricks, ways of proving things that pure mathematicians have developed over the centuries, millennia in some cases, that are very useful for proving things in computer theory, theory of computation, particularly in computability and, well, complexity theory as well. You'll see. It'll take a few months, but if you keep following this course, you will see many theorems, mathematical theorems, that are proved using the techniques that we'll do in this chapter 0, introducing proof techniques, methods, ways of proving. There are different methods, proof methods, that have been developed by pure mathematicians over many years in some cases. But these methods are very useful and used a lot, especially in this course, which I should remind you again, will become, be warned if you don't like such things, will become very mathematical. Right? You will think, you're saying, well, this is just pure mathematics. Well, yeah, it is sort of, but in the context of computing. Right? Remember how computing or computers got started. They got started from considering the mathematical logic foundations of mathematics itself. Right? Guys like Gödel and especially Turing, they were interested in the foundations of mathematics, and the notion of computability derived from that interest. Right? So when you're getting into the theory of computation, especially master's level, you are heavily into mathematics. It becomes pure mathematics. That's for sure. Which probably explains, like I was saying a session or two back, why theory of computation has the reputation in computer science departments as being the most difficult topic of the whole computer science curriculum, simply because it is very mathematical, and in time you will see that. But if you like math, and remember, I'm the deGarisMPC guy, right? I'm the guy who's trying to teach the planet topics, graduate level topics in math, physics, and a little bit of computing. So this computing is one of maybe only about 10% of the total courses in the whole deGarisMPC series, right, of all these math and physics and computing courses. So the computing side is more a minority interest. But this particular course is basic. If you really want to understand theory of computation, Sipser, the author, his text, Introduction to the Theory of Computation, is considered a classic. It's pretty well the Bible nowadays. Many universities around the world use this text because it's considered one of, if not the best. I mean, there are some other pretty good ones, but this one's gaining cult, C-U-L-T, cult status, meaning it's pretty much the Bible. Now, in general, for example, at master's level, M1 level, I will teach a course on classical mechanics as part of a physics course, well, physics and math course, a lot of math in it as well. Now, the text I will use for that is so much considered the Bible of its field, classical mechanics, that I don't really have much choice. I have to use that text because it's so widely used. Now, Sipser's book is getting that way. It takes time, but the textbook I'll use for classical mechanics is written by a guy called Goldstein, and it's considered the Bible in the field. So, in general, for all these courses, if there is a text that's generally considered to be the master, the best in its field, then I will use that text for several reasons. One, it's just then good, right? That's the reason why it is the Bible. It's just good, competent. And the other is because it's good, it's widely used, right? And then if I'm using a text that's widely used, you can probably pick it up more cheaply second-hand because there's a bigger market in that text. There's just greater accessibility. You'd be using the terminology, the notation used by that author, and therefore when you're talking with colleagues, it's likely they too will be familiar with that same notation and the text. So there's better communication with your colleagues. There's lots of reasons. So I tend to use classic texts, the Bibles, inverted commas, as far as possible. So that's one of the reasons for choosing Sipser, because it's getting that way. It's pretty much the most popular. Well, I'd argue. I haven't heard the actual statistics, but it wouldn't surprise me. The most popular text at master's level for theory of computation. But don't quote me on that. I'm not dead certain. Okay, so I'll stop there.